Let's give that a minute or so. All right, looks like it's working. All right. Let's see where we are. All right, looks like it's working. All right, okay. Let's see. So resources, again, just to make sure that you have access when you log in to your Canvas. The first module at the top of all the modules is a link to the syllabus. The syllabus gives a little bit of the agenda of what we're going to be following this week. Was mostly for installing MySQL and getting you going on the first assignment. So you know, from the questions we've been getting from on Piazza, it looks like everybody is working on that. That's great. Again, any communication that you want to ask us or any private messages, please stick to Piazza. Although you can reach out to us, obviously, on email and whatnot. But let's try and have just one single place where we have all our questions answered. We do have 8 TAs as well as myself that are, you know, watching Piazza like a hawk and trying to answer your questions. So please follow that. There are 2 Zoom. This one that started at 1:35. Although if you prefer to do the second lecture, that's fine. We are going to try and keep these as in sync as possible. So either one. Although for the quiz, I will ask you that you do come to the session that you're scheduled for, so that you know, if you have, you know, we're going to open it up for the first few minutes of the lecture, and you know, if you have any questions, that'll be perfect time for you to, you know, ask that questions about that quiz, about a particular question on the quiz. I did create a YouTube list, a playlist where I'm going to be adding all these lectures, and you should be available. You should be able to click on that, and that should take you to the videos where you can play them all. There's the one from last time we met, last session, right, where we talked about installing MySQL Server, and we created a table, we created a couple of records, we did some select statements. So it's all there available, and the video that we are recording right now should be available here as well. So you can either come here to this playlist, or my understanding is that they should be available also through your Zoom meetings. So if you go to your Zoom meetings, there should be a recording, cloud recording, that should show all the videos that all the lectures that we've had so far. Okay. And if you don't have access, please let me know. Apparently, sometimes there's a password, even though I've configured to not have a password. For some reason, it still has a password. But my understanding is that if you go there, it should copy the password in your and you should be able to paste it. This is just my general channel, and I would suggest you subscribe to my channel, where all the videos are going to be available. And if you subscribe and you press, I think there's like a bell, you can click on that, will notify you when new videos are made available. So, and if you do like the videos, please give it a thumbs up. All right. Let's see. What else? Okay. Office hours. These are the office hours. I have office hours on Tuesdays and Thursdays at 7:30. Please feel free to come by. Also, the TAs have their own office hours. Looks like most of the TAs have added their links to their particular Zoom meetings, although I think we're missing a couple. So the TAs will be sharing their office hours here in the office hours module. Okay, this week we've been focusing on installing the database. There's an assignment going on, and this is due on Tuesday, I believe. So this upcoming Tuesday, you should have you should have a MySQL server running locally on your machine. You will have created a table. I believe we ask you to create a users table. We ask you to insert a couple of users in there, I believe Alice and Bob, and then ask you to retrieve data from those records. And then at the end, we ask you to export the whole database and then share. I think it's like 4 files with us and submit that on Canvas. So that should be ongoing. You have all the weekend to finish this up, and we demoed the whole thing last time we met, last session. So if you want to review that, the video from last time, the last lecture, you could take a look at that and review it. We did demo the whole thing. Now, are there any questions from the assignment that is ongoing, or any questions at all? We can't answer here general questions about installation. That's we certainly can do that in the office hours. But are there any general questions about the ongoing assignment or the lecture in general?
Professor, for the names for the assignment, Alice and Bob, do you have to use those names, or can you use any names?
Really, you can use any name. I believe the assignments do ask you, I don't know, they ask to search a person by their username or their first name, Alice. As long as it shows that you knew what you were doing, you'll get full credit. Anything else? Let's see something on the chat. Should turn in the 4 files separately. I think it's easier for us if you upload the files individually. Unless for some reason Canvas doesn't allow you to upload individual files, then yes, you might need to zip it up. All right, so if there are no more questions, let's move on. Let's see. Let's talk about a little bit theoretically, in somewhat of an abstract sense, what databases are. Last session when we met, we were a little bit too down to earth, a little bit too hands-on. We demoed, installing a database and creating a table and inserting records and whatnot. And so we would like to step back a little bit and just talk databases in general, right? Where does it fit in the software engineering? What problems are they trying to solve? A little bit of the history and some of the challenges that all databases and any data storage solution will share with any different alternative that you might choose. Okay, so let's talk about databases and database systems in general, right? And then we can talk about specifically the relational database solutions that we are going to be talking about throughout the semester. But let's talk about databases in general first, and then we can focus on relational databases a little more specific. Okay. Okay, so let's talk about databases. Let's see, can I present? Okay, so let's talk about databases. All right, so what is a database, right? So database in general, right, is just a piece of software that gives us the capability of storing data and then be able to retrieve that data, right? And so it could be any different types of implementations we can think of, right? It could be just a file, right, that has different lines, and each line you have comma separated values that you can then write a program in Python or Java or any language to then read that file and then search through that file and return all the lines that meet a certain criteria. Okay, so it's a problem that has been with us for quite a while, since whenever we invented files and being able to read and write to a file. And so databases is the culmination of several techniques and technology that we have been developing so that we can optimize as much as possible being able to store data effectively, right, and be able to retrieve that data as fast as possible. Okay, obviously when you store data, and then the intention is that that data presumably represents some phenomenon, right? Some physical phenomenon, some real world phenomenon that describes some reality, right? Whether it's a list of your CDs, right? Your favorite songs, your contacts from your best friends. It could be some corporate information about clients and their employees, their salaries and the products that they sell, right? So we need to be able to identify what is it that we want to store. What is the best place, the best structure that we can store, organize that data, and how fast can we retrieve that data, presumably using some kind of criteria, right? So we want to store products, but then we want to say, well, out of the 3,000 products that we sell, can we identify what are our bestseller products, right? Then that means that presumably we're going to have not only products, but presumably we want to store also the orders, right? How folks have been ordering those products, and we'd like to be able to somehow aggregate how many of a particular product are folks buying, right? And then you can aggregate the number of orders for particular products, right? And then aggregate and say, okay, well, these are the bestseller, these are the top 10 best-selling products, right? Or these are the 10 worst products, right? And then you can say, well, let's phase out our worst ones and let's sell more of the ones that are successful, right? So certainly we would like our database to represent some reality of what's happening with our business, and depending on the kinds of queries and questions we can ask that data, it can be very important for us to make business decisions on where to take our business, right? So the more the database is a representation of reality, we will be making decisions based on reality, right? The more the database is not a representation of reality, then certainly we might be making decisions based on wrong information, right? So us as IT developers and software engineers is going to be our responsibility of making sure that the database, at least as a part of technology, will represent as accurate as possible, right? The reality of what we're trying to represent. That the database somehow models, right, a reality that we can then ask questions, we can run simulations, right, and then we can make decisions about that information. Okay. So a database is just basically a collection of data that we can store in a computer file system, in memory. Now we have some jargon here. Presumably what you store in a database presumably will be data sets, right, that are presumably going to be grouped into different types of things that you store, right? So for instance, here's my collection of employees, here are my collections of products, right? Here are my collections of orders. And so we can think of multiple bags of information where a particular bag of information is a collection of things that are like each other, right? So this is a collection of all my clients or all my products, right? They're all stored in one place and separate from each other, right? So there's my employees over here, and these are my products over there, right? And so all products are stored together. They are of the same type, and we refer to each individual product stored in that type. We call it a record, right? It's a point of data in that bag of data sets, right? That have similar features, right? All products might have a description, might have a price, might have a quantity that I have in store, right? That they might have a SKU number. Whereas the type of employees, right? I have the collection of all my employees, and they are also alike each other, right? They all have usernames and passwords and first names and last names and social security numbers and things like that, right? So each data point in that bag of collection of data, we call them records. Okay, and now that collection, that bag of data, depending on what technology are you using to store that, we might call it different things. If you're using a relational database, we say that is stored in a table. Okay, we create a table of employees, a table of products, right? A table of clients, right? And they all contain rows or records of clients, rows or records of products, rows or records of employees. Okay. Now each one of these data points in a particular type, right, are going to have fields, right, or attributes that are the same for each data point in that bag, right, of the same type. So for instance, here's an example of 5 different types of things that I would like to store, for instance, that you might find in a university. So if you go to any university, presumably you might find things such as students, departments, courses, sections, enrollments, right? And so we can think of these as you know, the collection of all the students, right? And each student instance, right, would be stored in maybe in a table of students, right? And presumably each data point in there will have the same attributes, right? Such as student IDs and student names and the year that they're going to graduate and the major that they're going to graduate in, right? Same thing for courses. In courses, you know, in a separate table, in a separate bag of data points, right, of records, you might have all the courses that might have a title, might have a course ID, might have the department that they belong to, right? So here is an example. These are 5 tables or 5 different types of things that I would like to keep track of, right? Now, you know, deciding what types do I care about, and what names I'm going to call those types, and what are the attributes, you know, making all those decisions is what we refer to as designing a database, right? Somebody had to decide that, hey, we're going to need a type of student, right, or type of department, or course, section, enrollment. Somebody had to make those decisions, right? And also the decisions of what attributes to put in there, and whether some things were strings, some things were dates, some things were integers and floats and whatnot. Somebody had to make those decisions. So making those decisions is what we refer to as designing the database. Okay. So here's an example of a small snippet of what a university database might look like. We have at the top, we have the collection of all the students. So these will be presumably records of all the students in a table called student. Okay. And these are different instances or records. So sometimes we might call them rows, right? If this is a table, then each one of these is a row, and each one of these are columns, right? The columns would be the fields or the attributes: major's ID, the graduation year, the student name, the student ID, and whatnot. Okay. Notice it's a very small university. It only has 9 students. It has 6 courses in total: DB, systems, compilers, calculus, algebra, acting, elocution. We have 3 departments: computer science, math, and drama. We have 3 sections for different courses. Now, notice that some of these values, course ID, looks like they are referencing, right, or they are referring to values in some other table with those values. See that? See where it says 12 here? This kind of says that this is a section that is being taught by Turing, that the section ID is 13, and it's a section for course number 12. See that over here? And it looks like we have 2 sections of this same course. So there are 2 DB systems courses. So somehow this data point here, taught by these 2 sections of Turing, are somehow related to this course over here. See that? We say that these two records are related to this one record over here. See that? So there seems to be like a one-to-many relationship here, right? And notice that I keep using the word relationship, right? And that's exactly why we call these a relational database, right? We are storing things in separate tables, but the records are somehow related to one another, right? And here's another example. We got two sections, one taught by Newton and one taught by Einstein, right? Of course, number 32. There it is, 32. See that? So it looks like the calculus course is being, one section is being taught by Newton, another one is taught by Einstein, right? And the elocution course is being taught by Brando. And see course number 62, and there's only one section of that, right? So the name relational database, which we're going to be spending most of our time in the semester, comes from the fact that we're going to break up different data pieces, right, in different tables, but those records in different tables are somewhat related to each other, and we relate them. We know that they're related because we're going to use values in one record, right, are going to be referencing values in another record, and we know that this course is somehow related to these two sections. Make sense? All right, excellent. Let's keep going. Yeah, so this particular university database, right, we have multiple data types. Okay, let's see something on the chat. When would records in a DB become archives? Archives, if are things that are not used often, we might archive them for later retrieval that we know, from previous semesters or years or decades, right? That we don't want to throw them away, right? But we know that our things are not going to be accessed as often as things that are much more recent. So we might archive them and put them perhaps in different drives. We could make archives mutable. Typically not. We make them so that we only see not changes, but we audit what modifications we might make, not in the original records, but we could have a log of the changes so that we can recreate any changes that we might want. But typically not, right? We archive it and they're only read-only for read-only purposes. So we're going to be spending quite a bit of time in this database. A lot of the examples that we're going to see throughout the semester are based in this university database, and so these are the data types that we're going to be using throughout. Right, we're going to have a student records, we're going to have enrollment records, course records for several sections, and so yeah, so deciding this structure of what tables and what attributes is designing the database. That's what we call designing the database. Database system is a collection of software that allows us to manage and store and retrieve and archive data. Right. In this particular case, it's the combination of SQL Server, MySQL Server that we installed last session, and the Workbench. Right. That is the client that allows us to have a client-server relationship between these two pieces of software, and allows us to manage our database, our data. Other attributes of databases that they are persistent, right? That they are meant for long-term storage, right? They're not meant for storage that comes and goes easily, right? It's meant that if you store it today, the data will be there tomorrow, right? As opposed to a piece of software that might run now, keep data in memory, in RAM, but then when that computer software dies, then and it comes up again, right? It might not remember what the particular state that it was in. Instead, databases are meant to store large amounts of data, terabytes, gigabytes, huge amounts of data for long-term storage, right? Also, typically, databases are meant to be used for amongst multiple users, right? So as opposed to a desktop application where you might be the only one who's using that desktop application using your particular RAM on your particular laptop, databases are meant to be used by hundreds, thousands, millions of users using the same database, sharing that, reading, mostly reading the data and for presentation purposes, and I want to view aggregations of that data. And millions of people might be querying your database and displaying it. It should be accurate, meaning we should feel confident that the data that is being stored there is an accurate representation of reality. right? That and of the correct granularity, and that it's appropriate for the particular domain that you are using, depending on what that domain might be. For instance, depending on whether you are the university or you might be Ford Motor Company, you might have different understandings or concepts of a vehicle or of a car, whereas the domain of a university, a car could be represented only perhaps as a make, model, the color, and the license plate, and maybe that's enough. In the domain of a university, it might not be enough if you're Ford Motor Company, right? That might be only the beginning, right? You might care also about the types of tires that you're using, right? The windshield wipers and the leather that you're using for your seats, and the steering wheel and all the knobs and all the the motors and all those things. So depending on what domain or what industry you're talking about, right? There might be different representations for the same exact concept, but it should be accurate and have enough information that is useful at the right granularity, that is useful for your particular application. Certainly should be usable. Even though we're talking about data that might be huge amounts of data, that might be obviously very cumbersome to try to consider all different pieces of information. You should be able to access the data. You should be able to query and ask questions from the database, and the database should be able to answer you, right? You should be able to aggregate and find out questions such as, how many courses did we teach this semester, and how many sections, and what was the average number of students in the sections, and and ask it questions, even though it might mean that you're accessing thousands, hundreds, millions of records that need to be aggregated and be able to answer questions, right? Usually there's this database administrator, right? Somebody who is responsible for the health of the database, right? That it's and that it the data is normalized, and that data is being stored correctly, right? And then that you don't have runaway memory leaks and things like that. Who is responsible for the health? The DBA is responsible for the health of the database. Okay. Storage of record storage, right? As when you're implementing databases, right? Early on, when we were thinking about how do we store things and then retrieve them, there were many iterations and evolution on different ways that we considered on how is it that we were going to store this data, right? In a file system, right? What do we mean by a record, right? If we know that a student has a unique student ID, has the name and the graduation year and the major, how do we store it? Do we store each student in a row, and then decide that each row has a different student? Somebody had to come up with those decisions on how is it that we're going to store it. Are we going to use just plain ASCII, right? Are we going to use binary? Are we going to, how are we going to separate one field to the next? Are we going to use tabs or commas? How are we going to separate each record? It's going to be a new line, right? So somebody had to come up with this with all these decisions, at the low level, how to store these different things, right? Perhaps it could be just a single file. In a single file, we store all the students in one file, and all the courses in another file, all the products in another file, and things like that, right? And now, obviously, many challenges would come up. It would be very, very slow to try and read these files one line at a time. You'll have to maybe load these files into memory and then search. And if you got to update something into a file, that turned out to be very, very, very slow, right? And so we've evolved many techniques on how to improve all these things. For instance, today we spread out the data into multiple files, right? And we also organize in such a way that make it easy for us to retrieve that data at some point later on by creating auxiliary files that are ordered in depending on how is it that you can search, that you want to search that file for, right? For instance, if you want to search, say, imagine using a a dictionary, right? A dictionary usually is organized in alphabetical order, right? Or even let's consider a phone book, right? Does anybody know what a phone book is? Probably not. Well, it used to be that you would have these large phone books where you would have listed in alphabetical order, right? By the last name of the person, if you want to find out what their phone numbers are, right? And it was organized by their last name, and because it was organized by last name, it was sorted. It was easy to find something if you knew the person's last name. Yes. And you could start in, if you knew their last name was Peterson, you would maybe start at the center of the phone book, right, and then either move left or right depending on the page that you open, right. And you could use search algorithms such as binary search, right. Eventually you move left, right, left, right, left, right. Eventually you would find Peterson. And now imagine that it was not sorted. Right? Maybe imagine it was not sorted. If it was not organized, then you could not apply the binary search algorithm. Right? Instead, you would have to start at the beginning. You start off with every single name, right, until you find the one you were looking for. That's a much less efficient way of searching. Right? One is linear search, and the other one is binary search. Right? And if you've taken algorithm class, you might have discovered that linear search is much slower than binary search, right? Linear search is linear, right? If you double the size of your search space, you double the time on average of finding something in there, as opposed to binary search, right? That if you double the size, you not necessarily you double the time for search, right? It increments very much slower and in a logarithmic fashion as opposed to linear, right? But somebody had to make the decision that we were going to sort it by last name. Imagine that it's organized and nice, sorted by last name, right? And I can use binary search for finding something really quick. But what if I don't have the last name? What if I have their phone number, right? If I have the phone number, I know that information is in the phone book, right? Because the phone book basically maps last names to phones, right? But if I have the last name, I could very easily use binary search to find it. But if I have the phone, right, even though it's organized by last name, it's really useless to me because what I have is a phone, right? So basically, even though it's organized by last name, I still have to use sequential linear search, right, one by one, looking for the phone number. Yes. So it'd be nice if you could have maybe two versions of the phone book, right? One that is organized by last name and another one that is organized by phone. Yes. And so I could use binary search depending on what I have. If I have the last name, I could use the one that's organized by last name, or if I have the phone number, I can use the one that's organized by phone. Now, these decisions on how to organize the data structure to improve searching through the data, right, is what we refer to as indexing, right? We can index these different data structures and organize it depending on what kind of searches, what kind of queries are we going to do in the data, right? And so indexing allows us to improve the performance based on the kinds of things we want to ask the database, right, and improve performance. Yeah, so multiple users. So as mentioned earlier, right, we're going to have hundreds, thousands, millions of people, accessing and updating and changing and inserting, removing data from the database. So if it were just you in your database, then there would be no problem, right? But imagine we're both editing the same Google document, right? And it's me and the TAs. We are working on an assignment, and I'm working way at the top in the introduction, and some of the TAs are working down at the bottom. We could have the risk of inconsistency. Say we're working on the same kind of area, right? I could overwrite somebody else's work, right? And somebody can overwrite mine. And so as long as we make sure that we are isolated, right, and say, well, you work at the top and you work at the bottom, right, then there's no problem, no risk of inconsistency. But what if we're working very close to one another? There could be a risk of overriding each other's values. So definitely databases need to consider this, right? Because in a particular table where you have thousands and millions of records, some folks will be editing some rows over here. Some folks are going to be editing some rows down there. But what if we're editing rows that are the same, right? Say I'm updating my balance. I'm depositing into my account at the same time that my wife is removing from the account, is withdrawing from that account, right? So what should the value of that account should be at the very end, after me withdrawing and depositing at the same time, right? What would happen? There could be some inconsistency there, right? So here's an example of an inconsistency. Some folks are multiple people are trying to book a plane ticket, right? And I'm at a website and I see that there are 40 seats left. It says, I got plenty of seats, right? And I book a seat and say, and what I see is that say two people are looking at the same time, and they both see that there are 40 seats left, and we both book the seats at the same time. What I see is that they went from 40 to 39, and what the other person also sees is that it went from 40 to 39. So from our point of view, there was only one seat that was updated, but in reality, there were two seats that were booked, right? So there could be that the database ends up in an inconsistent state because we were looking at it from two different places, and somebody has to reconcile, do a reconciling of all the data when you have multiple folks looking at the data from different points of view. So definitely databases need to take into account concurrency management, making sure that we're not both trampling on the same data, and decide how are we going to isolate all the changes that we're making. Okay, so and if there are consistency, the database needs to be able to detect those inconsistencies, right, and be able to retract itself and go back into a consistent state. Does it ever make sense to have multiple concurrent versions of a database with the same records but different designs that are optimized for different queries? Yes, well, we will be looking at that. Typically, you can have multiple representations of the same data using things such as views, and we will talk about that a little later in this presentation. Transaction is a mechanism that allows us to manage multiple folks, right? That if we are both of us are trying to access the same piece of information, one way to decide that, hey, you go first, I go later, and then we can isolate our change and we can serialize our updates, right, is through use of transactions. So transactions will allow us to do that. Single point of truth though. No, it won't. We'll see in a minute. Yeah, so transactions allows us to deal with isolating folks, dealing with accessing the same piece of information. Also, it might be that when we're making a decision or modifying something, we want to make sure that if we are dependent on multiple things occurring, right, we want to make sure that that all things might occur. So, for instance, say that I want to go visit my daughter in Chicago, and that entails many different things to come together if I'm going to actually decide to go and visit her, right? For instance, I might need to have three things might have to happen, right? I need to have a flight all ready to go, right? That meets my criteria of dates that I could go. I need a place to stay, a hotel, and maybe I'll need a car as well, right? And for me, from my point of view, all three things need to be successful for me to decide to go, right? So even though I might get, the flight is booked and I got my hotel booked, but I'm not going to have a car over there, then I might decide that not to go. So I need to be able to make those decisions, individually, right, and temporarily at least. Have some commitment from those folks that I am indeed going to have a flight. I'm indeed going to have a hotel. But for myself, right, the whole thing will go forward only if I also have the car. Otherwise, for me, the whole thing falls apart and I don't want any of it, right? So transactions allows us to do that, to group things that might be individually successful, right, but collectively might not be successful, right? So transactions allows us to group things together and decide whether we want to go forward or not if many things are not true. Also, databases allow us to manage authentication and authorization, allows us to say, identify ourselves and say that we are who we say we are. Obviously, if we're through login and whatnot. But in addition to that, not only authentication, oh yes, I know who you are, they also can allow or manage the authorization. Now, once I know who you are, I need to be able to set privileges for you, right? So I know who you are, so you have access to these tables, but not to these tables, right? Or you have read-only access to these type of information, but you cannot update, right? Or you can only read, but no write, no read. Okay, so databases allow us to configure those kinds of things as well. Memory management, right? So databases need to be able to manage their memory, right? Because they need to be able to map data that is stored in the file system that might contain millions, bazillions of records, right? Gigabytes, terabytes of records that obviously not all of it can be stored into the software, into a piece of software that might only have just a few gigabytes, right? Say the server might be able to peruse or go through millions of records, but the client can only ever just see or show us just a subset of those records, right? So the database needs to be able to make sure that it can optimize disk I/O, right? That it has to go fetch data from huge amounts of data into memory, and that obviously is not going to be able to load all of that memory into all that data into memory, right? It needs to be able to work with snippets of that data and then aggregate and collect the data as it goes, and work with smaller subsets of the data. So definitely databases need to do that. Also need to make sure that data is synchronized, right? Once you read from the file system into memory, right, the data is actually stored on the file system. Once you read it from the file system and you copy it into RAM for processing, for display, for whatever, right, there's always a risk of you working with stale data, right, with data that is no longer the actual data that is stored in the file system, right? Because you can read, copy it in RAM, but somebody else might be writing to it, right? Might be updating data. So you're working now in RAM with outdated data, right? And so any changes, any modifications, any decisions that you might be making will be based on something that's outdated, right? And so definitely the risk of inconsistency again, right? So data model. So by data model, we mean that we need to make a decision or a design on how is it that we're going to structure the data, right? And you decide what our data types are, what the different attributes and properties, and whether some things are going to be strings, integers, doubles, blah blah blah, blah, dates, booleans, and this is going to be represented in many different ways, right? If it's the file system, right, we might decide that the file system is binary, but represented in the database, it might be represented as tables and rows, and when we represent it in our object-oriented language, it will be classes and objects and things like that, right? Even though it's the same conceptually, it's the same data model, right, of deciding the data types and how things, conceptually they're the same, they have different representations, right? Depending on what domain are you talking about, okay? So the file system, right, it might have the, the schema and how it's broken up into multiple databases and the different files and the indexes and how it's broken up into whether it's binary or ASCII or whatnot. Or you have a relational data model where you're talking about tables and records and relationships between these records. So even though it's representing the same data model, right, it will be represented or implemented in different ways. Also, we have or we might have decided that the representation is in XML or JSON or comma-separated values, right? The physical model and how it's being stored, right? It could be in proprietary format, right? Some proprietary binary format, right? Or something as easily that can be read as a comma-separated value. Depending on the representation, right? Way back before we had databases, we might need to write proprietary code such as this, right? That would read a file system, right? Would read each line from the file system, iterate over all those lines, and parse all the strings, split and then compare all the values that it's looking for and do aggregation values, right? And then come back with a result. Okay. Today we have evolved and we have generalized this solution into what we call databases today. So instead of this query, which is doing what? It's getting all the students from 1997, right, by reading from a CSV file and looking for the graduation year to be 1997, and adding and creating an array of strings of the users or the students. Today we can do things such as do a query where we can say, select the name for the students where the year is 1997. Right, so certainly we have come a long way of being able to not have to think about the physical implementation, the physical representation of the data, but instead we can talk about it in a much more conceptual model, using the relational model where we're talking about the table students containing fields such as student names and graduation, and then we can do comparisons and we can use queries such as select name from student. Right, so we've come a long way in creating all these layers of abstraction that allows us to think about the data in a much higher abstract way. Now, there's many different ways, as I mentioned earlier, there are many different ways of representing the same data. There's graph databases, there's object-oriented data models, there's hierarchical data models, right, whether using XML or using Java classes or C# classes. But typically they would represent the different ways of representing the same thing. So databases allow try to provide an independence from how the data is actually stored in the database, right? We don't really care how the actual vendor specific format that the database is stored in the physical system, where we want to be independent of that. Instead, we want to create a conceptual or relational model that allows us to think about it, in terms of some higher abstractions such as tables, rows, and records, right? Now, we also want logical independence in that underneath we might decide that we break it up into students, courses, sections, enrollments. We decide that that's the best way to organize it. Yes, but some folks, depending on their use, the data they use, might find it cumbersome to use that representation, depending on the queries that they might want, right? So for instance, the registrar's office might decide that, hey, at the end of the semester, I want to aggregate, I want to find out, what were the top 10 best sections, things like that. Well, that would mean that I need to aggregate information that is in the sections table, along with the enrollments table, along with the students information, right? And I need to do those three queries, aggregate all the records, find the ones that are related, and do a roll-up of all that data. It's very, very cumbersome, right? So most databases provide what is called a three-level architecture, where you have at the bottom, you have the physical schema, right? That has the actual file system, the physical files that might be in binary format, right? That are not meant to be read by human beings. Then you have the middle tier here, which is the how we decided to break up the data, right? That we're going to have a student table, we're going to have an enrollment table, we're going to have a section table, the course table, the departments table, right? But then you might have a third layer above it, which we call the external schema, right? That I think this goes to what our colleague was asking, right? This is a representation and a different representation of the data, but based on the underlying structure that is already there. Typically, this is implemented using views, and what views are a wrapper, right, or a reusable query, right, that we might often use to aggregate data, to roll up and create reports, right, that grab information from this table, records that are related to this section with that other table over there, right, and and then thousands and thousands of records are then collated into just a few set of resulting results that we can use for a report, right? That could be used maybe by the dean's office, maybe by the faculty or registrar's office, that we want to aggregate all these thousands, millions of records into some few set of information that I can distill and then create a report. Okay. Now the source of truth is still the same, right? It's the same tables, the same records down below, but they're aggregated into a more convenient view. Sorry for the redundancy. We aggregate it into a useful view for different audience, right? For the audience that wants to consume the data in a much more convenient way. Okay, and certainly MySQL provides this this mechanism, and we will certainly spend some time on implementing these. We're first going to spend quite a bit designing this first, what these tables might be and how they relate to one another, and then we'll spend another week, deciding on how to implement these views for creating reports, aggregations and whatnot that might be useful for different audiences. Okay. All right. So that was a very, very high level, introduction of databases. Very, very theoretical. We're certainly going to get into much more nitty-gritty detail on what all this means, and in the next weeks ahead. Okay. So yeah, so if you feel a little bit overwhelmed, we're going to be spending about a week or so in each one of these different concepts that we've been discussing. Right. The first thing that we'll talk about is how to design. How is it that you design? How is it that we decided that we need a student table, an enrollments table, a sections table, right? So what how is it that you came up with that idea, right? So we'll come back. Well, that's what we're going to be. We'll start talking about it today a little bit, and then we'll focus it quite a bit next week. And also there's a whole assignment on designing the database. Okay. Then we'll talk about transactions and views and data retrieval and updates and whatnot. Any questions so far?
I have a question about how the SQL text gets compiled or interpreted by the server. How does that process happen?
So there's what is called a query planner, and so all you write your query at a high level English like query, which needs to be converted into something that can be executed, right? And it's somewhat similar to what we'll look a little bit later called relational algebra, that basically is broken up into actual functions that are going to be executed in a particular sequence, right? That depending on how the data is going to flow through several transformation functions, right? And so we need to identify what those functions are. Like obviously there's a select function, there's a projection function, there's a renaming function, there's quite a few of them, and we'll talk about that when we visit relational algebra. Relational algebra preceded the creation of SQL, right? SQL just happens to be one particular implementation of the relational algebra. But basically what the transformation is that we transform the English-like query into a relational algebra equivalent that can then be executed sequentially, retrieving the data, then selecting it, then renaming it, then projecting it, and doing all these transformations until you get a result set. And yeah, so we'll talk about that a little later.
Thank you.
All right, so let's see. Just wanna make sure. All right, so let's talk about data design. Okay. Okay, so as I mentioned earlier, there are many different ways of representing data. Okay, you might represent data using some high-level object-oriented language, right? Whether it's Java, C++, C#, something in the chat. Let's see. Are these slides available on Canvas? Yes, I got them from Canvas. If you go and yeah, I'm looking at this right here, UML class diagrams. Right, so if you click here, you should get this right here. Chat. Week 2. Oh, it's blocked? Really? Oh, okay. Let me unblock it. There we go. You should be able to see it now. Okay, where do you see it now?
Yep, looks good.
All right. Okay, so let's see. So there are many different ways of representing data, depending what you're doing, right? If you are implementing a desktop application, then you'll need to represent data, perhaps using some Java classes or C# classes, right? From where you can then create instances of these of whatever you are trying to work with, right? Or if you're trying to represent it in a file system or document, then you might use XML or JSON or comma separated values, different ways of representing that. Or if this is something that you're doing it graphically in a spreadsheet, then you have rows and columns, and you might have multiple spreadsheets that somehow are related to one another, right? Or you might decide that you are using a relational database where you have tables and records and views and how they're related to one another. So depending what you're doing, there are literally infinite ways that you can decide how you want to represent data. Okay, and they might be all equivalent, right? If you have a Java class that has a user Java class, in there you might have a properties in there called username, password, first name, last name, all strings, maybe date of birth, date. But then if you want to represent the same thing in a relational database, you might have a table, also called users. The naming conventions might be different. Okay, the data types might be slightly different, but conceptually they're the same thing. Okay, that you might also have fields in there, username, password, first name, last name. The naming convention might be slight. You might use underscores in one. You might use camel casing in the other. The relational databases, typically you might need a primary key, but you don't need it in an object-oriented language. If you're using spreadsheets, you might have rows and columns, and each column you have the fields, right? So you might have a column username, a column last name, a column first name, a column date of birth, right? And then each row for you is a record, right? So yeah, I mean, there are literally infinite ways that you can decide on how to represent this data conceptually. Okay, I'm sorry, in a concrete fashion, you can decide on representing it in many different ways. So we need to come up with a standard way of representing this data that is independent of how you're going to be implementing this. It should be independent of any of the technology choices that you have out there. Something that it goes across all technologies, across any backgrounds that you might have. That some folks are front-end developers, other folks are data analysts, some folks are business analysts. Excuse me. Some folks are middle tier developers, whatever. Okay, so we're going to be using a way of representing data called UML. Okay, so UML stands for Unified Modeling Language, right? It's a language that is universally accepted as a standard for representing or diagramming, right, with boxes and arrows, right, on how to talk about data. How is the data organized, right? How is it structured, okay? And so we're going to be spending about a week or so, starting today and all next week, talking about how is it that we can represent data using this conceptual, diagrams that allows us to represent all sorts of things that are data related. Okay, it turns out to be the best way of starting, right? So that in general, whether you're developing programs or you're developing databases or whatever you're doing, chances are that the best place to start is with a UML diagram. Okay, you would first design a high-level. You would use a high-level modeling language such as UML, right? And then try to represent your high-level representation into a lower level. Into a language, right, that can represent those diagrams, right? Whether you use Java or Python or C++, C#, whatever, right? And then this gets compiled down to either JVM, GRE to actually implement and run this in your system. Or if you're developing databases as well, right? The appropriate thing to do is to start off with something really, really high level modeling language that allows us to implement, design this, talk about it at a high level, right? And then map that into a lower level language such as SQL or ER models, right? And then finally, the database system executes all these. So any of these approaches, they all start with UML, right? It's a lingua franca, right? It's a language that goes across the various barriers of technology and backgrounds that we might have, so that we can discuss this, even though we might come from different backgrounds. Okay, so one of the UML is heavily based on object-oriented fundamentals, right? The fundamental part of an object-oriented language is what we call the class, right? And the class, well, let's say the object, sorry. The object is a particular instance of some fundamental concept that has a specific set of properties that are common to a subclass or a group of data points that are like foundation or a concept, right? So when we are describing an employee or describing a course or describing a product, right? We all have the same kinds of properties, right? So you might be describing a particular product, but that some other specific product might have the same attributes such as the SKU, the description, the price, and things like that, right? And so the way we talk about it as being part of the same thing, about the same type, we say that they're all part of the same class. So class is what allows us to represent particular instances of objects as being part of the same concept, right? And typically we use singular nouns or noun phrases, right, to name these classes or these data types. Now, usually we also describe not only the data types, the type of a piece of information, such as first name, last name, and whatnot. We also typically describe the behaviors, the methods, and functionality that a particular class might have. Right now, from the database point of view, we're going to drop this second part of this. Right, if you've seen classes in other courses, typically you describe both things, not only the attributes, right, and the data types, but you also describe the behaviors. In our class, since we're not this is not a programming course that you're instantiating these classes and whatnot. And instead, we are only caring about the data portion of it. We're going to drop the method definitions, right? So the official way that we're going to represent these classes is what we call a class diagram, right? So here's an example of a class diagram, which we're going to use to represent the conceptual model, data model, right? It's basically a box, right? That has three sections, three portions. The first one is the name of the class. The second part is the attributes, right? So for instance, the name might be product, right? And the attributes might be price, description, the SKU, right? How many do we have in stock? Right? So those are all different attributes of product. If this would be a person, then you might have first name, last name, right? Middle name. You might have some profile information such as email and things like that, right? That describe a client or a customer or a particular user. Now down below, there's a third section that again we're going to ignore in our course, in our database course. We're going to ignore, but typically a class diagram would also down below also have behaviors or functions or methods, right? That encapsulate the verbs that are associated with that particular noun. So for instance, if this is an account, say you have an account, the account might have a balance, right? The date that it was opened, right? The last day that it was accessed, things like that, right? And then it would have behaviors associated to that account, things such as deposit or withdraw or close the account, or transfer from one account to another. Now we're going to ignore these methods, right? Because we don't care about these in a database setting, right? So all the class diagrams that we're going to be focusing in this class are only going to have two parts, right? It's going to have the name of the class and the attributes and the types, right? And so the syntax here is that you have the attributes, their data types, certain things are strings, dates, Boolean, integers, floats, and whatnot. These over here at the on the left-hand side, you have these pluses and hash signs and minus signs. What they mean is the accessibility of these attributes to outsiders, right? So if you have 2 or 3 classes here in your model, right, you want to also capture whether one class can access attributes in another class, right? By plus, we mean that it is accessible, it's public, right? Anybody can access it. By minus, we mean that it's private, meaning nobody can access this data, right? It's only private to the class. And then we have the hash, which means that only those that inherit from me can access this value. Nobody outside of the inheritance tree. Now, we don't really care about these accessibilities modifiers, so you can safely ignore these. You can make them all pluses, all minus, doesn't matter. A good practice, right, by default, is to make them all private. Okay, so many tools that we're going to be using, by default, they use minus, and that's totally fine. One tool that I use that is proven very useful is Visual Paradigm. Visual Paradigm is a tool that allows you to create UML class diagrams, all sorts of class diagrams. I'm sorry, all sorts of UML diagrams, of which classes diagrams are just one of them. And so let me just show you. So here's an example of a class diagram that we're going to be using in our upcoming assignment. Okay, so for instance, here we have many classes. We have the user class, which by the way, this maps to a table that you're already creating for this particular assignment, right? You're creating a users table, yes? And that users table might have things such as first names and last names, usernames and passwords. So these are attributes that you are going to be implementing in an upcoming assignment, right? And in class diagrams, we say that these are strings, right? Which in a relational database, you implement them as varchar, okay? Now, designing it using class diagrams is a much easier way to think about the data instead of thinking about it in terms of tables and columns and rows. Right? It's very, very hard to visualize in your head, tables, right, and how they're related to one another. But if you have a graphical representation of the data, it's much, much easier to understand how the data is structured. Okay, so we're going to spend about a week or so talking about class diagrams and all sorts of things that you can do. For instance, these one-to-manys and these loops over here, right, and what these stars mean, and what these enumerations mean over here, okay? So we're going to spend about a week or so talking about this. Now, you might have seen some of this in other courses. You might have not. I am going to assume that you have not seen this before, okay? Since this is an undergraduate level course, you might have seen this maybe in 4500. You might have seen this, maybe, I don't know. So I'm not going to assume that you've seen this, right? My assumption is you've not seen this, and I'm going to treat it that way. Okay, so class diagrams. So we're going to spend some time in doing class diagrams. So here's an example of a class diagram representing a person. The person might use a username and a password. Here's this date over here, this date of birth. This 01. What this says is that it's optional. You might have a date of birth. You might not have a date of birth. It doesn't mean that you're not born or not or whatever. But we might not know the date of birth, so it's optional. That's what it means. It's 01. It could be there. It could not be there. Multiplicity means that how many instances of one thing are participating in a relationship. Okay, so for instance, here in this diagram, right? In this diagram, we have this this user, right? And we have this blog, right? So we're going to be implementing an application that allows folks to create kind of like a social networking system, or maybe like a blogging application. And so a user might create many blogs. Right, so I might have a blog that is about, rockets, another blog that talks about cars, maybe another blog that talks about music. So as a user, I can create many blogs, and there it is. See, this 1 and star mean that one user can be related to many blogs. Okay, so that's what these two things mean, right? And we call this cardinality, or how many of one thing are related to other things. Okay, and now the cardinality we can say this star, right? This star means we don't know how many. There could be 0 blogs. Maybe you just logged in and you haven't created any blogs yet, right? So this could be 0, or it could be 100 blogs. We don't know. So that's what star means. Or if we know, or we have a limit on how many there are, right? We can do things such as, well, you can have 4 blogs, right? And what that means is that you have exactly 4 blogs. Now, this might make sense or not, right? That we limit folks at having 4 blogs and that's it, okay? Or we could say that you can have a minimum of 2 blogs all the way up to 4. So there's a range, right? You can have between 2 and 4 blogs, right? So we usually use this nomenclature. It's n.m. So it's a minimum and a maximum. Okay, but here we're going to say star because we don't know how many blogs you might have. You might have 0 or more. Okay, so yeah, so we can denote it using m.n, right, or star. Okay, there's a few of them, few common multiplicities we might use. 0.1 means that it's optional, right? So if we say here that this is 0.1, it means that this blog is optional. You can have 0 or 1, meaning you can have 1 blog or no blogs. Okay, so let's leave it at star. Let's see something on the chat. Is there a difference of 0.star and 1? I think you meant maybe 1 ... star. Yes. So yes, there is. So 0 ... star is the same thing as star. Okay, star is an abbreviation of 0 ... star, which means 0 or more. But if you have 1 ... star, it means that you have at least one, right? You have to have at least one or more. So it's 1 or more or 0 or more. Okay, so yes, they are distinct. And actually, I believe there's a quiz question somewhere in there at some point. So hint, hint, careful. There might be a quiz question where it asks you about the difference. So if it says, instead of 0, 1, can I just write 1? No. If you say 0 or 1, it means that a 0 is an option, meaning I might not have one. But if you say 1, that means it's required. You have to have 1 at least. Okay? So yeah. Yeah, 0 ... 1 means it's optional. It could be there, it could not be there. Whereas if you write 1, means that you have to have at least 1. Okay? Yeah, at most 1. Okay. Any number of values, 0 or more, or 1 or more, at least 1 value. Yeah, it says right here. Enumerations. Okay, so like any language, there are limitations of what the language can do. Okay, so most of the times we can represent data things with classes, right? We represent posts, right, or whatnot, right? But sometimes there are things that are not representable by a class diagram. So the language allows mechanisms for extending the language, such as things that are not representable, right? And the way that they do it is by creating what are called annotations, right? So see these pointy brackets over here, pointy brackets. That means that these are classes. These are classes, and you don't have to tell me this is a class, right? Because that's what they are. I mean, that's the standard. But this over here, it's a box, right? It's a box, has a noun, right? There's some things listed there, but this is not a class. So you should not interpret this as a class. Instead, you should interpret it as whatever it says here it is. In my case here, I'm saying that this is not a class. This is an enumeration. It's an enumeration. And enumerations, like you might have seen in Java or C# or in other programming languages, what it is that it allows you to list values that are valid for that particular type. So for instance, you might have an enumeration. Let me see. Hello? Okay, so here's the enumeration. And let's create an enumeration here. And the enumeration might be genre, right? Like movie genres, okay? And I want to enumerate all the valid values for a genre. And you might have one of the genres might be that it's horror. That's a valid genre. One might be comedy, right? Another one might be sci-fi. So we're creating a brand new data type called genre that if I make a variable, right, that if I create a variable for a movie, say, so if I say movie, that's a movie, and the movie might have a title that obviously is a title and needs to be a string, but it should have a genre, right? And what type could this be? Well, I could say string, and then people can just type in the genre, horror, comedy, sci-fi, whatever. They can actually type it, right? But that's error prone, right? That could be error prone because you could type any string, right? So we want to make sure that this is validated, that you're giving me valid values for this genre. So instead of making it so general like a string, we could say that this is of type genre, meaning that the only possible valid values for the variable genre could be only one of these three. That makes sense? Okay. So this enumeration is because this is enumeration, it should not be interpreted as a class. A class says I have fields title and fields genre. These are variables title and variable genre that can have values. Here, horror is not an attribute. It is not a field. Okay, instead, it is a value of the data type genre. It is a value that can be assigned to a variable. That makes sense? Okay. So yeah, so that's what an enumeration is. And enumeration is not a standard concept in UML. That's why you can create your own things, and you can create them and name them whatever you want, and then you have to explain to people what does this mean, right? How this should be interpreted. And we know what enumeration is because I just explained it to you. Okay, so this is how you make enumerations using stereotypes. Also, things that are very common in object orientation are things such as specialization and generalization. Okay, where you can have base classes, right? So let's create here another. Let's create here a class diagram for this class, new class diagram. So we'll call this 3200 SP21 section 03. Okay, and so you could have classes such as. Is there a question in the chat? What if the value of a field is an object with multiple attributes? Yep, exactly. Let's do that. You create yeah, exactly. So say you have here. Say you have. Let's go back to the class diagram that we had earlier here. Social. For instance, you have a user, and you want an attribute. You have an attribute address. Okay. Now this could be a string. This could be a string, and that string then can have address 1, address 2. You can have a zip code and city and state, blah 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 blah. You can type the whole string here, or you could be a little better, right? And you can create a whole new class that is called address that can have all sorts of things in here, right? That you can have. Address 1, that is a string, street address 1, so address 2, which is also string. You can have city, which is a string. You can have state, which is a string, right? And you can have zip, it could be another string, right? And then address here, instead of this declaring as a generic string, you can say address is of type address. Okay? Yeah, perfect. And then you can have this relationships, right? There would be a there would be a one-to-one relationship. You'd say that a user, one user can have 0 or 1 address. So it's optional. You don't have to give me an address. Okay, that makes sense? All right. Okay. Yeah, so generalization and specialization allows us to describe things that can be started off with something very abstract, and then you can specify things that are a little more specific. Okay, so for instance, you might have a class that might be called shape. Right, and shape might be a little bit too abstract, right? And for instance, you might have things such as the name of your shape, which is a string. You might have the size. You might have the color of the shape. You might have position of the shape. Okay, but if somebody asks you, okay, draw me that shape. Would you be able to draw that shape? Probably not. Okay, you would need to know more information about it. Now, there are many types of shapes, and how would you capture that? Well, you can capture it using generalization. Okay, and so you can have maybe a rectangle shape, right? And or you can have that has all the attributes of a shape, right? It has a name, a size, a color, and a position, right? But it can add things such as width and height, okay? And things such as area. Well, no, actually, everybody has an area, right? Let me delete that. But width and height are specific to a rectangle. Or you might have another shape, right? That might be a circle. And circle has attributes that are the same as a shape, but are distinct from the rectangle, right? It could have things such as, might have things such as radius, okay? It could have a circumference and things like that, right? So you see how this allows us to reuse concepts, right? Inherit all these concepts to define things that are more specialized, right? So this is shape is a generalization of a circle, and circle is a specialization of a shape. Make sense? Rectangle is a special case of shape, and shape is a general concept from rectangle. Make sense? Let's see, are there questions in the chat? If you have 2 to n, does the field become a list array? Yes, yes. All these things become, right, when you have multiple things of something, then they are arrays. So yeah, let me go back and talk about that. Socialize here, social, right? So for instance, here we have one-to-many, right? So user has many replies, a user has many blogs. So the way this is implemented in Java is that you would have an attribute, something like this, called blogs, and then this would be an array of blog, like that. Okay, that's how you would implement it in Java. But UML is it's a concept, it's conceptual, that it's it tries not to make not to capture anything that is specific to the underlying implementation. Okay, this here is redundant because this line over here already says that for one user there are many blogs. Okay, so this is kind of saying the same thing, right? But it's specific to the programming language of Java or C# or C++, right? Because to implement it, that's how you would implement the one-to-many, right? There's one user has many blogs, and the way you implement that is through arrays. The way you implement it in SQL, in a relational database, you would not have arrays. Instead, you would implement it by having here an attribute, another attribute that you say who the user is. Okay, which is a reference back to the user. Say, oh, I am the blog for that user. Okay, so that's how you would implement it in a relational database. But again, UML doesn't really care or should not care about the specific implementation technology, whether it's Java or relational databases or XML or whatever, right? Those are all details of implementation. This line already tells me that there's one user for many blogs, so it would be redundant to put this here. Now, I would maybe put it anyway sometimes. You would decide to maybe put it there, even though you know it's redundant, right? You would probably put it in there only for clarification, right? Only if it makes the diagram a little more understandable for your audience, right? If your audience is a Java audience, then yes, put the array in there. If your audience is a relational database audience, then yes, put the foreign key over here. And we'll talk about foreign keys later in the class. Make sense? But from the UML's point of view and conceptually, this line over here is plenty, is enough to say that one is related to many. That answer your question? Yeah, arrays. Okay. All right, so let's keep going. Something in the chat. Yes, thanks. Okay. So here's an example in this slide, right? We have a widget here, and you know, this might be a widget that you'd be dragging onto a page, right? And that widget might be an image widget or a YouTube video widget, right? And all widgets have a name, all widgets have a width and a height, but an image has, you know, where to fetch the file for the image, right? Whether it's a JPEG or PNG or whatever, or if it's a video, YouTube video, then the URL of that video, right? Now, notice that here we've used a stereotype. See that the pointy brackets, right? It's pointy brackets. We're saying that this is a class. This is a class, right? It has attributes and it has data types, but it's an abstract class. What we mean by abstract class is that I don't have enough information here, right, in this class to actually create an instance of that class, right? Very much like our example here in our, this example here, this shape over here would be an example of an abstract class, okay? Because say you want to try and draw this on the screen. Could you draw this on the screen? You couldn't, right? So it would make no sense for you to have an array of shapes, okay, that actually have instances of shapes in there, right? Because, you know, if you try to iterate over that array, you're not going to be able to draw it, anything, right? Instead, you would have instances of rectangles, instances of circle, which you then iterate over, and then you put your circle at that position. You have the radius, right? And you can draw that circle. So circle and rectangle, we would say these are concrete classes that can be instantiated and acted upon. Whereas shape would be an abstract class, right? That could not be instantiated. You cannot create an instance of that, right? And again, you might have seen some of this material in previous courses. I'm not sure what course you're coming from. But again, I don't want to assume that you know all these concepts, and so I'm going to treat this as, you know, brand new to you. Actually, I'd love to hear. I don't know, how do you do a poll? I would like to make a poll. Maybe some. Oh, there it is. Poll. I had a question. Geez, is that complicated, huh? Enter a title poll. How many of you have, okay, how confident are you with UML class diagrams? That is a question. Multiple choice, answer 1. We'll say 0, 1, 2, 3, 4, or 5. 0, 0, none, 5, expert. Okay. Oh, no, that's all the one I want. Delete. Save. All right, launch. I'm going to launch that poll, and if you could answer that, I'd like to know how do you feel with UML, and if this is if this is totally boring to you. Okay, I see that quite a few feel somewhat confident. That's excellent. Perfect. We've done 87%, 90%. Okay, looks like this hopefully is mostly a review for you. So 93% voted. Okay, let's see, chat. It was covered in Fundies 2. Fundies 2, okay, excellent, very good. All right, I'll end the poll. Did you cover it, this with us in OD? Oh, I did? Okay. Let me end the poll. Excellent, thank you. All right, it's good, it's good. All right, excellent. Let's keep going. Why is this more in the chat? And it's in IS 2000. Okay, perfect. Why can't I interact with this? What's going on? Reload. Uh-oh. Hello. I think I've lost my slides. What's going on? Let's see if I can relaunch my slides here. Class there. Okay. All right. I don't know what happened to this tab here. I'm just going to close that. All right, classes. Right, so what else? So some fields, as some folks were mentioning, right, could be arrays, right? And you can have many tags. A post can have many tags, could be multiple strings. Also here in the, you can use, in general, the lines that connect two classes, we call it an association, right? That we say that one class is associated to another class, and that usually we label the two classes and specifying what kind of role each one of the classes is playing in this association. For instance, we might say that an author, if you have an author in a book, we might say that an author writes the book, right? And you can start off by the class and read the name of that role as you read it from that class to the other class. So we say a book is written by an author. Okay. Yeah, so you read it starting off from the class towards the other class. We also we can also associate and put we can put the cardinality next to each one of the associations, and specify how many of those are participating in the interrelationship, right? Like 0 or more authors are participating with one or many books, right? Okay, so you also have what are called association classes. So association classes are somewhat like a mapping, right? Where you might say that many of some, right, are related to many of others, right? So for instance, here's an example. Here's an example, right, going back to these social here. So here's an example where you might have this blog rating. Okay, I think this is backwards. I have this backwards. This is start here. This is a 1. Okay. So this is saying, for instance, that a user, right? And you have a post. So somebody says, post something on the internet, right? In a blog, and a user reads it, and they can like the post, right? So for instance, here's a rating. You can either like the post, or maybe you can leave a comment for that post, or maybe you can score it, right? And you give it a star. You have a 5-star rating, right? You can tell me how much you want to give it, right? And so what this is saying is that these users, one user can have many ratings of a particular post, right? Or I'm sorry, a user can rate many posts, and a post can be rated by many users, right? It's kind of like a many-to-many, right? Saying that there's a relationship of one user to many posts, and there's a relationship between one post and many users, right? Which makes sense, right? Where one user can like a whole bunch of posts, right? And one post can be liked by many users. So this over here, this rating is a many-to-many, right? That says which users are related to which posts. And that relationship, I am describing it, saying, hey, that relationship between this particular user, and that particular post, that this user likes that post, right? And that this user gave it this score, okay? Now, if the relationship is only a many-to-many, right? It's only a many-to-many, and it doesn't have any other attributes, we typically, this is the way you would draw it. Okay, you have a 1-to-many and a many-to-1, right? Going from user to post. Okay. Now, in newer versions of UML, if you have attributes, the way you draw it is using this nomenclature. Okay, where you have author and book. This is a many-to-many. Okay, but because there are attributes, you would capture it using this association class like this. You have one line between the author and the book, and then you have this association with this dotted line. Okay, here one way that I should have captured it is using the association, because I do have multiple attributes here. In the older UML, which I'm using here, you use this nomenclature, one-to-many and then many-to-one. Right, but in the newer UML, the way you capture it is that you have one line going from user to post. Okay, and I guess we can show you this here. Okay, let's create here another. Let's create a blog here, and this might be this is a reader, right? And you have maybe a book, and they're reading a book. Okay, and then here you can make an association. So many, and this might be many readers read many books. Okay, and then I forget how do you do the association. How do you do associations? I don't remember. Is it here? No. I forget how to do the association using this tool. So anyways, would be dotted line here, and somebody might be doing a review of the book. Okay, and you might say, you might give it a score. How much do you like that book? And then you might give it a review as a string, saying, "Oh, this book is terrible. Don't buy it." Okay. So if you have fields, then the proper way of capturing this would be a dotted line going across. Okay. If you don't have any fields, then the proper way of capturing it is the way that I capture it here. Right? You have just a mapping table or a class going from left to right, right, with no fields. Okay. But this is just a newer version of UML. Capturing it this way is also appropriate, and I will accept either one. Okay. Aggregation. So aggregation means that there's a relationship between the two, between the classes. There's a one-to-many relationship, right? One to several. But in addition, I want to capture the fact that there might be a life dependency between the two. Okay. So for instance, say I have a product and I have orders, right? So let's go back here, and let's go back to class here, and you have a product, and you have many orders. You have many orders, right? Order. And so one product can have many orders. Right? Now, what happens if I remove the product? Now, if I remove the product, typically, I would also want to remove the order. Makes sense, right? So there's a life dependency between the product. It would make no sense to keep around an order, right, if the product was removed. So there's a life dependency, right? If I remove the parent, then the child goes away as well, right? But what if it's the other way around, right? Say I have the order and I have the product. What if I remove the order? Would I also remove the product? That makes no sense, right? That means that the order, there's no life dependency between the order and the product. Okay, there's a life dependency going from product to order, but not from order to product. You see that? Right? Meaning that the order might have maybe a reference to the product, meaning I am an order for that product, right? And that if I remove the order, it does not propagate to my reference. Okay. But the other way around, it could be true, right? The product might have references to the order that if I remove the product, that propagates down to the other ones, right? So aggregation and association, this aggregation allows to document the fact that there is no life dependency. If I remove a page, do I also remove the widgets? Or maybe you do. If you remove the page, yes, I want to remove all the widgets. So this says if I remove the page, I do not remove the widgets. Whereas this says that if I remove the page, that propagates down to the widget and it goes away. And we capture that by what we call composition. Composition captures the fact that there is a life dependency. One is composed of the other. Okay. All right. I think we ran out of time. We'll continue and pick this up on Tuesday. All right. Awesome. Thank you, everyone.
Thank you.
Thank you, Professor.
Thanks, Professor.
All right. Take care. Bye-bye.
Thank you.